Alrighty, good morning, lads and ladies. Welcome back to Calc 1. Today, we're going to kind of button up our conversation on differentiation rules. And I'm going to talk a little bit about the test. So, let's do it. Use QCam. Now, I got to warn you, my pens are kind of all dying. And I'm in the process of moving right now, so things are a little bit hectic, a little bit messy. If I have to change colors at random times, or things look a little bit weird today, I apologize in advance. This purple is a lie. This blue works, but it I think is a little bit light. So. Lies. All right, we'll make do with this. So yeah, a few things. Some announcements. I'm afraid today's office hour is canceled. I've got a bunch of meetings in the afternoon, and I also am in the middle of moving. I got to get completely moved out of this house, so I don't really have time to move it to a different time. Remind me, did I have a meeting with anybody about student teaching today? I know, Chris, we talked about it recently. I don't remember. I think yours was going to be next week, right? But I just want to make sure I'm not messing up any major plans. So did anybody have a meeting with me this afternoon that we needed to talk about? I'll add an extra one. Office hour next week. Either Monday or Tuesday. Correct me if I'm wrong, but Chris, we were going to meet early next week, right? That was the plan?
Yeah, I believe it's Wednesday, the 10th.
Okay, cool. And nobody else had a scheduled thing with me this afternoon, right? If we did, don't be afraid of contradicting me. I'm sorry if I forgot. If we did have something scheduled this afternoon, please let me know now so we can plan. All right, sweet. Exam 1 is going to be next Wednesday. So it's going to be during class time. This is 2:10. Some things I need you guys to do to prepare for this is please download Zoom on your phone if you haven't already. On the day of the test, I'm going to need you to Zoom into a meeting, and and we'll be so I can see your desk and your workspace. So you'll be using both Zoom and HonorLock. So please also make sure that you have HonorLock on your laptop or computer. And make sure Chrome is up to date. Yeah, study guide should be up on WebAssign. I think you guys took a little bit longer. Like I posted the Calc 2 study guide to your thing originally, and I really do apologize for that. But I had to pull it down and then post the correct one. So it did take a little bit longer than I anticipated. But yeah, it's up there. It's up there on WebAssign. It's been there since I think yesterday morning. The study guides you should. So right here, study guide 1. is up on WebAssign. Remember, the way you get the points for the study guide is by writing out the solutions to your problems. Submit those on Canvas. And do those as quickly as you can. So the idea is that I would like you guys, ideally, to all have your study guides submitted like by Monday, so I can get in there and make comments, you know, and tell you, hey, if this was on a test, this would be a half-point mistake, or on a test, this would be a 1-point mistake, or, you know, this all looks beautiful, keep doing it exactly like this, or don't worry about simplifying that. All of those little sort of things that people want to know while they're taking a test, I want to be able to answer those questions for you ahead of time on your study guide. So please go ahead and as soon as you can, get working on the study guide. Your solutions don't have to be perfect or neat or anything like that. They just have to be, you know, legible. So, you know, don't worry about like copying them back down or anything along those lines. Just write your work as you go and then submit your work after you finish. And I'll get in there and make comments as soon as I can. The last day to turn in the study guide, well, let me say it like this. No, the study guide is due at the start of the test. Right. Ideally, you would submit it long before then, because if you hand it in right at the start of the test, you're not going to be able to get any comments or feedback on your work. So I really want you guys to submit the study guide as soon as you can. Monday would be good. But yeah, I will still take it up to the start of the test. So if you submit it 10 seconds before the test starts, that's okay with me. You'll still get the points for it, but you're not going to get the feedback in time for it to be helpful to the test. So ideally, you'd submit it no later than Monday. What else do we need to talk about along these lines? Office hour, exam 1, study guide 1. Well, I think we're good there. So there are a few problems that I wanted to look at that kind of explore a little more deeply some of the concepts we've been messing with. And the first thing I want to do is look at some of these special trig limits. So we have lim x to 0 sine x over x. This is 1. And lim x to 0 cos x minus 1 over x. This is 0. These can be used to figure out other limits. And I know I did an example with some of you guys in office hours yesterday, so I don't want to be super redundant. I'll just do one now. For example, the limit as t goes to 0 in sine 5t over 3t. Class times for the test are normal. So what I'll do is I'll actually have the test open about 15 minutes before class starts, and it will go to about 15 minutes after class ends. That's to help with any technology problems. I'll post an announcement with very detailed instructions. Basically what it's going to say is 15 minutes before class, sign into Zoom on your phone, come to this Zoom meeting where I'll sort you guys all into separate breakout rooms. So you can't see each other's screens, but I can see yours. And then you're going to, once we're okay in Zoom and we've got everything set up so I can see your desks and we're all happy with that, then you're going to go into Canvas on your computer and you're going to launch the test. And that will start you through the honor lock process. Honor lock's going to like look at your ID, scan the room, blah, blah, blah. and then you'll start on the test. So I want you guys to sign in a few minutes early, a few minutes before class starts if possible. But if that's absolutely not possible because you've got other shit going on right up to the start of this class, I'm also allowing a few minutes extra at the end. But it will be normal class time. This is what's called a synchronous online class rather than an asynchronous online class. And synchronous classes like this, sync classes, have to do exams at regular class time. So it will be the same class time as normal, but I'm going to open things probably at like 10:45, and I'll let them run probably until around 12:30. Okay, so coming back to this. The trick to these sort of things is to make them look as much as possible like this. And it already looks quite a lot like that. I've got sine of something over something else, and I'm setting the variable to 0 here. So this looks like this. This kind of looks like this. And so I'm hoping that I'm able to deduce the limit. Maybe it's 1, maybe it's something else like that. The real key to this sine x over x limit, you've seen me do it as sine h over h and sine theta over theta. The real key is that the thing down here is the same as the thing in here, and that both of those things are going towards 0. Up here, the 5t inside the sine function, there's really no way to get rid of this 5. I can't like pop him out. That sort of shit never works with trigonometry, right? The sine function's like a little box and you can't really get things out. We have special identities for some cases like sine of 2t. We have a double angle identity, but we definitely don't have like a multiple of 5 angle identity. But the 3 down here, he is able to move around. So my first step here is going to be multiplying by 5 over 5 and then doing some sneaky algebra. So I'll write this as sine 5t over 3t. And then I'm going to multiply by 1 in the clever form 5 over 5. And then I'm going to shuffle the 3's and the 5's around. So this is lim t to 0. Sine of 5t over, I could call this 15t down here if I wanted, but my long-term goal is to get the 3 out and the 5 in. So I'm going to say this is 5t, and I can do that as long as I bring the 3 over here, just because of the way fractions multiply, right? Now, if you look at this expression, it's looking more and more like this. I've got sine of some stuff over that same stuff, right? Sine of 5t over 5t. And the technical way to do this is to make a little substitution. I would let x be 5t. And note that as t goes to 0, so does x, i.e., x goes to 0 too. So this limit as t goes to 0, sine 5t over 5t can be rewritten as limit x goes to 0, sine x over x. And then the 5/3 here is still just hanging out. And the limit as x goes to 0, sine x over x, that's 1. So this whole piece right here is 1. So I get 1 times 5/3. And 1 times 5/3 on a good day, that's 5/3. And you may notice a little pattern here. So all of the special trig limits that are in your homework for this week follow from this same stuff, right? This is the trick. You've got one that involves a sine and a tangent. You might have one that involves the cosine. They're all going to use this same sort of trick where you need to do some algebra to make it look as much like your special trig limit as possible, and then you make a substitution. Now it's worth noting that if this was like sine of e to the t over e to the t, I couldn't use this trick because as t goes to 0, e to the t goes to 1. So if I tried to make the substitution x equals e to the t, I couldn't say that x goes to 0 as t goes to 0. So it's important that you kind of pay attention to the substitution here. The section in the textbook works one or two of these as example problems, and this is the way that they do it. But I just want to emphasize that it's the fact that, that x and t here do the same thing, because x is 5t, as if t is 0, x is 0 as well. Any questions on this one? Okay. If the sine were a tangent instead, I would break it up into sines and cosines. There is a little thing that you can discover here, and one of the themes of the problems I want to work today is sort of pattern recognition. So I would say try to prove that the limit as t goes to 0, sine of at over bt is always going to be a over b. And similarly for tangent, sine as t goes to 0 of tangent of at over bt also goes to a over b, using the same techniques. Discussed here. It's not too hard. And I think once you have a good feel for this, it'll help with some of the sections that we're going to talk about down the line. It'll definitely help in Calc 2 when we talk about the limit comparison test, and it'll help here when we talk about differentials and approximation. I'll be able to make some analogies if you really understand this in a deep way. The next few problems I wanted to work with, again, like I said, have to do with pattern recognition. So are there any questions on this?
Can you do the tangent one?
Sure, we can take a look at one of the tangent ones. Maybe I'll use a different variable here. Let me use theta. Say lim theta to 0, tangent of 4 theta over the sine of 7 theta or something like this. I don't want to spoil the whole thing for you because this isn't your homework and it is a fun problem. But my first steps would be to write tangent as sine over cosine. So this is sine 4 theta over cos 4 theta, all divided by sine of 7 theta. And then to sort of split this up, we'll just do some algebra here. This is lim theta to 0. Dividing by sine 7 theta like this is the same as sine 4 theta over cos 4 theta times 1 over sine of 7 theta. And then I can do another kind of splitting up with the sines and cosines. So I would say that this is sine of 4 theta over 1 times 1 over cos of 4 theta times 1 over sine of 7 theta. And now with each of the sine pieces, my goal is to use that special trig limit, the sine x over x. So I need a 4 theta down here to pair with the 4 theta up here. And I want a 7 theta up here to pair with the 7 theta down there. So first what I would do is I'd say I'm going to multiply by theta over theta. One of these, the upstairs one, I'm going to put over here. And the other one, the downstairs one, I'm going to put over here. So I'll get limit theta to 0 sine 4 theta over theta times 1 over the cos of 4 theta times theta over the sine of 7 theta. And now we're getting close. I want to observe that the middle term here really isn't consequential. As theta goes to 0, this piece is going to become the cosine of 0, right? Cosine of 4 times 0. What is the cosine of 0? Yeah, it's 1. Katie's got it in chat. Cos of 0 is 1. So this whole piece is just going to 1. He's like not hard to figure out. He doesn't have any problems with like 0 over 0 or any of that shit. So the cosine term really isn't interesting. Now I want a 4 theta down here. I've got a theta down here. So I'll multiply by a 4 down here. I can do that as long as I multiply by a 4 up here. And then I've got my 1 over cos 4 theta. Again, I don't really give a shit about him. I want a 7 theta up here to pair with the 7 theta down there. So I'll multiply by a 7 up here. And that means I need to multiply by a 1/7 here. So we haven't done the sine AT over BT proof. I'm asking you guys to work through that. I say that it's the same as the problems we did. I can flip the page back over and you can look at the specific one that we did. But we're almost here with this problem now. So my next step would be to give the limit to these pieces separately. Lim theta to 0, sine 4 theta over 4 theta times 4 times lim theta to 0, 1 over cos 4 theta, this piece is boring, times lim theta to 0, 7 theta over sine 7 theta times 1/7. So this first piece here is about done, right? I've got sine of something over that thing. I'll make a substitution. This piece will now go to 1. This piece was always going to 1. He was never exciting because the cosine of 0 is 1. This is just 1 over 1. And this piece requires a little bit of attention. And what I would do is I would say, all right, this is lim theta to 0, sine 4 theta over 4 theta times 4 times lim theta to 0, 1 over cos 4 theta times lim theta to 0. I'm going to take the reciprocal and then raise it to the negative first. So that makes this look like my sine x over x, and then the 1/7 is here. So in this guy, I'll make the substitution x equals 4 theta. So x goes to 0 as theta goes to 0. And over here, I'll make the substitution z equals 7 theta. So z goes to 0 as theta goes to 0. All right, and each of these are still being multiplied like this. And now that first guy becomes lim x to 0, sine x over x. And then I have the 4 here. This piece right here is just 1. All right, it's 1 over the cosine of 0, which is 1. And then this piece over here is going to be lim z to 0, sine of z over z to the negative first times 1/7. So I've got this special trig limit here and this special trig limit here. And this guy is just 1, because 1 over the cosine of 0 is 1. So the first bracketed expression goes to 1. So this is 1 times 4 times 1 times this piece right here goes to 1 to the negative first power, which is also 1. And then the 1/7 is the 1/7. So at the end of the day, I've got 1 times 4 times 1 times 1 over 1 times 1/7, which is 4/7. And that's the procedure. They take a little while to write out. This particular one with the tangent is kind of complicated, but it's just the same trick that we used on the previous problem twice, right? We're using it here. Where is it? All right, we split everything up, and then we use that trick here and here. I think kind of the sneaky thing with this problem is that you have to introduce not just the constants, but also these thetas, right? If you go up one more line, we didn't originally have the variable downstairs. I multiplied by theta over theta after splitting everything up to get started. Okay, I'll hold here for about 5 seconds and then I'll flip back to the previous page. Yeah, sure. Okay. So here was the previous page. This is sort of the simpler example. All right, so once you've mastered this one, then try that tangent one. That's the idea. Yeah, there is no, the problem that I wanted you to prove? Yeah, down here, try to prove these things. So what works here for the sine works here for tangent as well. Sine and tangent near 0 are actually very similar to each other. That's kind of what this is showing. Is that if you look near 0, sine and tangent actually do the same shit. I zoom way in. Right? They look so similar. And the closer you are to 0, the more similar they are. And you get away from 0, of course, they're very different animals. But sine and tangent near 0 are both very, very similar. In particular, both of them have the tangent line y equals x at 0. And that's what we're getting at here. But we'll talk way more about that sort of stuff when we talk about linear approximation and differentials. For now, I want to go ahead and move on to the other sort of pattern seeking problems that I thought you guys might enjoy for the day. And so let's do it. So I want to find the 99th derivative of sine and the 35th derivative of x sine x. And both of these have like shitty solutions and nice solutions. The obvious shitty solution is to differentiate the sine function 99 times. Don't do that, right? Nobody should do that. But if we start looking for patterns, the first derivative of sine is cos. The second derivative of sine is the derivative of the first derivative. So that's the derivative of cos, which is negative sine x. And then the third derivative should be the derivative of the second derivative. So that's the derivative of negative sine x. Now the derivative of sine x is cos x, so this is going to be negative cos x. And the fourth derivative of sine is the derivative of the previous line. And the derivative of negative cos x, well, the derivative of cos x is negative sine x. So the negative of that is positive sine x. And you notice that we are back to where we started with, right? And so the fifth derivative is the same as the first derivative, which is cos x. And there's a bunch of fun things we can talk about here. What's going on here is that these these derivatives cycle every 4 derivatives, right? You take the derivative 4 times and you're back where you started with. You're back to the original. Have you ever seen something like this? Suho had a really dope pre-calculus class. Have you ever seen something like this where every 4 iterations you start back where you began? This might not appear to be directly related, but the imaginary number I satisfies I to the 0 is 1, I to the 1 is I squared is negative 1, I cubed is I squared times I, so that's negative I, and I to the 4 is back to 1 again. This repeating every cycle of 4 is the same as the repeating every cycle of 4 here. In fact, you'll even notice that the pluses and minuses, like if you swap 1 for cosine and I for sine, these look very much the same. And that, my friends, is not a coincidence. There is a really deep connection between derivatives of the sine function and powers of I. It's a consequence of something called Euler's formula, which I'll be able to prove for you at the end of Calc 2. So I'll just say this is similar to powers of I. So a fun question that some people like to put on their pre-calculus tests is, compute the 150th power of I. Computing the 99th derivative of sine is really the same sort of thing. So how could I figure out the 99th derivative of the sine function? Any thoughts here? Yeah, something like this, right? So every 4 derivatives, you start over again. Now 99 isn't divisible by 4. If 99 was divisible by 4, like the 4th derivative of sine is sine. The 8th derivative of sine is sine. The 12th derivative of sine is sine. Every 4 derivatives you start back over. So instead of thinking of this list as going down and down and down here, just think of it as cycling around. We want to know, if you take 99 steps, where do you land in this cycle? Are you sine, cos, negative cos, or sine, right? Where do you land in this cycle after 99 steps? Yeah, Katie's got it here. It's about remainders. And this is something to do called modular arithmetic. I think the best practical way to do this, especially if you haven't seen this stuff before, is to ask, well, where are we in the 100th derivative? Because 100 is divisible by 4, right? The 100th derivative of sine is going to be sine. It means you walked through the cycle here. Here's the cycle. It means you walked through this cycle 25 times. You differentiate sine 100 times. So the 100th derivative of sine is the same as the 4th derivative of sine. So what is the 99th derivative of sine? Good, negative cos x. It's the same as the third. If 100 is the same as 4, then 99 is the same as 3. Or you could think of it another way. 96 is divisible by 4. So you know that 96 is the same, the 96th derivative is the same as not differentiating at all. So 97th derivative would be cosine, 98th derivative would be negative sine, and the 99th derivative would be back to negative cosine. It's true that 99 is divisible by 3, but that doesn't really help here because the length of the cycle is 4. So I need to find out where I am in this cycle. So I need to know, how far am I past the nearest multiple of 4? Or how far am I back from the nearest multiple of 4? And in this case, I think we're 1 less than a multiple of 4. So the 4th derivative would be the same as the 100th derivative, which means that the 99th derivative should be the same as the 3rd derivative. It's a coincidence that the 3rd place here happens to be, like, I get what you're saying, Kevin, that 99 is divisible by 3, and maybe that's linked to us being at the 3rd point in the cycle, but that's actually not the same. What's going on here is something called modular arithmetic. It's all about remainders. And what we noticed here is that 99 is equal to 100 minus 1, which is 4 times 25 minus 1. So we could say 99 is congruent to negative 1 modulo 4. So in other words, if you're running through a cycle of length 4, that's the same as being 1 back from the end. If you take 99 steps running through a cycle of length 4, that's the same as being in the 3rd position. Negative 1 and 3 are congruent mod 4. I invite you to Google this, modular arithmetic. The particular branch of mathematics that I work in, called number theory, is obsessed with modular arithmetic. It's the basis for most abstract algebra. It's a really beautiful thing. If you want to talk about finite fields, then you reduce all integers modulo your favorite prime. And that will give you a finite field, meaning a place where you can do addition, subtraction, multiplication, and division, just like the real numbers. Finite fields are very special if people are interested in elliptic curve cryptography, those sort of things. All right, so we found the 99th derivative of sine. The 99th derivative of sine is negative cosine, because 99 is congruent to 3 mod 4. And that means we're in the third row of this 4-row cycle. The other one's a little harder. I want to find the 35th derivative of x sine x. It's harder because there's a product rule here. But again, we're going to be looking for patterns. So the first derivative, let me write it like this actually. The 0th derivative of x sine x, if I don't differentiate at all, that is x sine x. The first derivative of x sine x, this is a product rule thing. I differentiate the x, that gives me a 1, so I'll have 1 sine x plus, now I leave the x alone and I differentiate the sine x. So the first derivative is 1 sine x plus x cos x. The second derivative, d2 dx squared of x sine x, I need to differentiate the thing above. So the derivative of sine is cos x plus, now here I need the derivative of x cos x, which is going to be 1 times cos x plus x times the derivative of cos x, which is negative sine x. And so this is 2 cos x minus x sine x. And you notice something kind of interesting happening, right? We tend to have an x sine x or an x cos x piece lingering at the end here. And then I've got 0 sine x, 1 sine x, 2 cos x. There's a number counting up over there. Let's look at the third derivative. The derivative of 2 cos x is negative 2 sine x minus the derivative of x sine x. Oh, well, I've calculated that earlier. The derivative of x sine x is sine x plus x cos x. So if I combine these, 2 sine x minus sine x is minus 3 sine x. And then I have plus x cos x. Oh, let me see something here. This is subtracting, right? Minus, yeah. Hang on. The derivative of x sine x is plus x cos x. Yeah, I need to, sorry. There's a negative here that needs to distribute. This is going to be negative. Sorry about that. And we continue. So my fourth derivative, d4 dx to the 4 of x sine x, I get by differentiating the line above. The derivative of negative 3 sine x is negative 3 cos x. And then I'll have minus the derivative of x cos x. The derivative of x cos x, I've calculated that before also. That I calculated here using the product rule is cos x minus x sine x. So if I simplify this a little bit, I'll have minus 3 cos x minus cos x. That's minus 4 cos x. And then I'll have plus x sine x, distributing that negative. So we've got our first 4 derivatives here. The first derivative here, second derivative here, third derivative here, fourth derivative here. 1, 2, 3, and 4. Do we notice any patterns? There's one thing I'm sure everybody's seeing, and that's these numbers, right? 1, 2, 3, 4. And they're following the same plus and minus pattern that we saw in the last guy, positive, positive, negative, negative, positive, positive, negative, negative. So what do we think the fifth derivative would look like? Let's do this without calculation. Let's try to deduce this from the pattern. We conjecture that this is, well, there's going to be a 5 here. Is it going to be positive or negative according to the pattern that we've got so far?
Positive.
Yeah, good, positive, right? Because we went plus, plus, minus, minus. Next will be plus, plus. So, and then we've got sine, cos, sine, cos. So what's going to go here?
Sine of x.
Good, sine, yeah, because all of the odd derivatives have a sign in this position. All right, now what about the other pieces? This is plus, minus, minus, plus. What do we think?
Plus x times cosine.
Good, yeah, this is also a 4 cycle. We just started in a 1 position rather than in a 0 position. If you look up here, you can think of this first guy as being 0 cos x plus 1 x sine x. So plus, plus, minus, minus, plus, plus. And then again, we're going sine, cos, sine, cos, sine. So this is going to be x cos x. And we get that just by looking at patterns, right? No actual calculation. So if I wanted to figure out the 99th, oh, sorry, no, what am I looking for here? The 35th, sorry. 35th derivative, d35 dx to 35 of x sine x. Where am I going to land in this whole array here? Well, I'll say I'm going to have a 35 here, and then either sine or cosine, and then I'm going to have either a plus or minus, and then an x sine cos x or x sine x, one of those. So the question is here, is this a plus or a minus? Here, is this a plus or a minus? And then we know that this is going to be an x times some trig function. So in each of these slots, is it going to be sine or cosine? Let's figure out the first slot here. In the 35th derivative, is that first blank, the blank after the 35, going to be a sine or a cosine, and why?
Cosine.
Good, yeah, cosine. For what reason?
Because 36 would be going through the cycle 9 times. So subtract 1 from 36.
That works, yeah. Or another way to say this is that if you look at the patterns here, so the first derivative, we had a sine here. The second derivative, we had a cosine here. The third derivative, we had a sine here. The fourth derivative, we had a cosine here. The fifth derivative, we have a sine here. All of the odd derivatives, like 1, 3, and 5, you have a sine there. So this is going to be a 35 sine x. And I know this because the odd derivatives all have sine here. Okay. What about here? What about the second blank there?
Plus x sine.
Yeah, this one's going to be a cosine. The same sort of logic, right? All of the odd derivatives in that second spot have an x cos x. And this is because all the odd derivatives have x cos x here. So now the plus and minuses, these are the fun parts, right? And this is where we really do need to think about those cycles of length 4. The pattern appears to be plus, plus, minus, minus, plus, plus, minus, minus. It's a cycle of length 4. And the nearest multiple of 4 is 36, right? 36 is a multiple of 4. So the 36th entry, would that be positive or negative in the first term? Or where is the 36th entry in this pattern? Yeah, 36 is the same as 4, right? So 36 should have the plus in the first, or sorry, the minus in the first and the plus in the second. So 35 is 1 back, should have the minus in both. Another way to think of this is that 32, if you want to go back to 32, 32 is also a multiple of 4, should be the same as this. So if I want to get from 32 to 35, I need to walk forwards 3 steps. So this is 32, 33, 34, 35. So it's going to be minus and minus in both of these. And these guys are because 35 is congruent to 3 modulo 4. So we know we are going to be in the 3rd row. And that's it. So these sort of things are a lot of fun. The modular arithmetic that underlies them is really beautiful. And it's something that's worth studying if you want to, if you're interested in number theory, if you're interested in the sort of pattern stuff, if you're interested in cryptography or any of the places that that sort of thinking can take you, modular arithmetic is the right place to start. It's also sometimes called clock arithmetic. The Wikipedia page is very good. And what we're really doing here is just looking mod 4. All right, everything that we're looking at, probably powers of I are here. Oh no, maybe not, I'm not sure. Nah, all right, but that's okay. So really what's going on here is every 4 we reset. We're wrapping around, we're running through a cycle. And that's true for the signs, the SIGN signs of each of these. It's true for the sin x cos x patterns here and the x sin x cos x patterns here. But the numbers out front, those just count up, right? So we know the 35th derivative has to have a 35 here. And then everything else, all the rest of the structure of this derivative really does follow from thinking about the mod 4 pattern. If you want to check, you can. Tools that are good for checking this sort of thing. I know there's lots of other ones, but Wolfram is still the nicest. So we could ask for the 35th derivative of x sine x. And you'll see here it really is negative 35 sine x minus x cos x, as we deduced. All right. We have a handful of minutes left here. These were the last few things I really wanted to show you guys. So what would y'all like to look at? Are there any problems in the homework that are driving you nuts or anything that I don't want to taint the study guides. I want to see what you guys really do with that. But if there are any homework problems you guys would like to look at, I'd be happy to look at those now. No, I wouldn't think of the study guide as covering it all. Really, the homework is the first place to start. So Katie asked, what should we review for the test, which is a fair question. I would say, first and foremost, the homework, right? The homework problems should be your main focus. You should make sure that you really are comfortable solving all of those homework problems, except anything that requires you to like guess, right? There were a few problems in the homework where you had to look at a graph and you couldn't quite tell what the Y value was and it told you to estimate. Don't stress those. But aside from those, the homework problems are by far the most important tool. Make sure you're comfortable with all the example problems we do in lecture. Those are also very important. And then once you're certain you're comfortable with those, then the study guide problems are a good thing to practice as well. The study guide isn't meant to be especially challenging. The study guide is meant to be kind of like gentle problems that ask for those same skills. So I can look at your work and give you feedback on the basics with the study guide. The test problems will be around the difficulty of the study guide, but there will be a little bit more work to do on the test than there is in the study guide. So I would say focus on the homework first. And then knock out the study guide, being aware that the study guide problems are meant to be somewhat easy, not super hard. And the same is true of the test problems. They're meant to be somewhat easy, not super hard. But if you really want to beef up your skills and make sure you are ready to rock the shit out of this test, the best thing you can do, and this is true for all math classes, is open up the book and make sure you can solve the hard problems from each section. Right? So if you really want to make sure that you're going to destroy this thing, come in here and look for the problems that look scary, look for the problems that look hard, and then try to solve those. And the standard advice really is to solve all the problems in the book. But yeah, I would say homework and study guides first, then start going through book problems and look for ones that look hard. Yeah, we can look at number 13. Don't tell me this goddamn thing kicking me out every 10 minutes. Of course. Okay, you guys are here. We want to do number 13. Yeah, this is fun. So these springs, harmonic oscillation. That's what's going on here. Is everybody comfy with the kind of physical thing that is going on? Basically, you've got, their diagram is fine, but you've got a wall over here. And then attached to that wall is a spring. And at the end of that spring is like a rolling mass or a sliding mass, something that has no friction. There's an equilibrium position here, right? Like if I don't touch the thing, if I just leave it alone, then it's gonna sit there. But if I pull this out and then let go, it's gonna start bouncing back and forth. And if there's no friction here and no energy lost to thermodynamics, you call it like air resistance or heat, if no energy is lost, then it'll bounce back and forth according to like a sinusoid pattern. It would be like this, which if you turn over is a sine wave. So they're saying that the equation of motion here the position of the oscillating mass is given by 4 sine t. Yeah. And they want velocity, acceleration, and then all three at time 2 pi over 3. Hamlet, stop it. Be good, Bubba. Velocity, remember, is the first derivative taken with respect to time of the position. So that's d dt of 4 sine t. The 4 is a constant multiple, so it's going to come along for the ride. And the derivative of sine t is cos t. So the velocity function here is just 4 cos t. And acceleration, thinking about what is acceleration, it's how quickly you're speeding up or how quickly you're slowing down. It's the rate of change of your velocity. So that's the derivative of your velocity function, which is the second derivative of your position. Now we already calculated the velocity. The velocity is 4 cos t. So if I want acceleration, that's the derivative of velocity. I just differentiate 4 cos t. And that's going to be 4 times negative sine t, or negative 4 times the sine of t. Right? Because the derivative of cosine is negative sine. And the 4 comes along for the ride. And those are being multiplied. So 4 times negative sine t is negative 4 sine t. Now they ask us to do a few things. Find the position, velocity, and acceleration at time 2 pi over 3. So at time t equals 2 pi over 3, this is just about knowing the unit circle. X of 2 pi over 3 is 4 times the sine of 2 pi over 3. What is the sine of 2 pi over 3? Here's pi over 3. 2 pi over 3 is the symmetric point over here. Yeah, so the sine value up there, the point here is 1/2 comma root 3 over, sorry, negative 1/2 comma root 3 over 2. So this is 4 times root 3 over 2. And then you can cancel the 4 and the 2 a little bit there, and you get 2 root 3. The velocity at this time, I just plug 2 pi over 3 into my velocity function. So this is 4 times the cosine of 2 pi over 3, which is 4 times, according to this, negative 1/2. So that's negative 2. And my acceleration at time 2 pi over 3 is negative 4 times the sine of 2 pi over 3, because my acceleration function is negative 4 sine t. And again, the sine of 2 pi over 3 is root 3 over 2, so this is negative 4 times the square root of 3 over 2, which is negative 2 root 3. So, fun question. If my velocity is negative and my acceleration is negative, what's going on? Yeah, so the fact that the velocity is negative means we're heading in the negative direction. And the fact that the acceleration is also negative means that we're speeding up in that negative direction. So if the velocity and the acceleration are pointing in the same way, then you're speeding up. And if your velocity and acceleration are pointing in the same way, in opposite ways, then you're slowing down. So velocity is -2. This means I'm going to the left. And acceleration being negative as well means I'm going to the left and speeding up. So we're moving in the negative direction and we are speeding up. Oh, here, and this is pretty much the last thing that they ask us, right? So what direction is it moving at that time? Since the velocity of 2 pi at 2 pi over 3 is negative, right, less than 0, the particle must be moving in the negative direction, which is to the left. That's it. And the fact that the acceleration is also negative, we could use to say that this is speeding up. If the velocity were negative and the acceleration were positive, then we would be slowing down. Does that make sense? Okay, cool. Yeah, these are fun problems. They are. We have about 7 minutes left. So are there any other problems that you guys would like to look at before we finish for the day? All right, then I want to leave you with something here, something to think about. This is a true statement that I can't prove to you yet, but I'll be able to prove to you in Calc 2, and I just want to show you. E to the ix, this is the same as the cosine of x plus I times the sine of x. Just go with it. Like a bad acid trip, just go with it. This is weird. All right, who knows what the hell it means to take a number like e and raise it to I times some other number. This is bizarro shit. Admittedly, very strange. It has a bunch of funny consequences. But now that we have the chain rule, I can show you what I was talking about. Because the left-hand side here is a chain rule derivative. I is a constant. So the derivative of e to the ix is e to the ix times the derivative of ix. And over here, the derivative of cosine is negative sine x. Plus, again, I is a constant, so the derivative of I sine x is I cos x. The derivative of ix is just I, so this is I times e to the ix, and that is negative sine x plus I cos x. But now this piece, you know, is the same as cos x plus I sine x, so I could set those equal to each other. And you can imagine how if I repeatedly differentiate, if I took d dx of I e to the ix, this would give me I squared e to the ix. And d dx of that would give me I cubed e to the ix. So the fact that the sines and cosines cycle through plus and minuses the way they do as you differentiate really is a consequence of the powers of I being what they are. I squared is -1. I cubed is -I. And on the right-hand side over here, we can start writing down the derivatives of sine and cosine. So I'm certainly not going to test you on this, but I just wanted to show it to you. This is an amazing thing called Euler's formula. And besides all of this, one of my favorite consequences of Euler's formula, if you plug in pi, then you get the statement e to the I pi is equal to cos pi plus I times the sine of pi. You may have seen this on a shirt or two of mine. This is e to the I pi equals -1 plus I times 0. And anything times 0 is 0, add the 1 over, and you get e to the I pi plus 1 equals 0, which is also sometimes called Euler's identity or Euler's formula. Many people consider this to be one of the more beautiful expressions in mathematics. And as utterly bizarre as it is, like what the hell does it mean to take pi, multiply by I, and then shove that in the exponent of e, it really is true that if you do that and then add 1, you'll get 0. This is neat for a number of reasons. It has all of the important constants, e, I, pi, 1, and 0. It has all of the important operations like equality, addition, multiplication, exponentiation. And it shows the interplay between these really important constants and really important arithmetic operations in a way that is kind of mind-blowing. I didn't believe this the first time I saw it. I really didn't. Someone showed this to me and I was like, you're lying. Like, you're clearly just fucking with me. But it turns out to be true, and it's a consequence of this, which we will be able to prove about 2/3 of the way through Calc 2. So I hope you're enjoying what we're doing so far, and I hope that this kind of tantalizes you a little bit. The connections between those sort of pattern finding problems, which are really like counting problems, problems to do with combinatorics and patterns and cycles, can be connected in a really beautiful way to calculus, which has nothing to do with like counting or discrete math problems. And this is, I think, the place where most mathematicians get hooked, is starting to see a connection between very different styles of mathematics, realizing that calculus can help you with number theory, for example, or realizing that combinatorics can help you with functional analysis, realizing that studying power series can somehow tell you something about the geometry of space-time. It's all pretty mind-blowing, and a lot of it starts to feel serious right around here. So I hope that you guys enjoy working through the problems in the study guide. None of those should be too hard. Do finish up the homework as well. Try to get that done. And then make sure you submit the work for your study guide problems as soon as you finish them. That way I can get in there and give you some feedback. Again, there's not going to be an office hour this afternoon, but I will add an extra office hour next week. And that is all from me today, guys. So I hope you have a lovely rest of your day. If you are getting close to your student teaching day, please do work hard on preparing those materials. Also, that is important, not just for you, but for your classmates to make sure they have a good experience then too. All right, I'm around if you need me. Canvas messages are the best way to get a hold of me for now. I'll be clearing out my email a little later today. And that is it. Take care, guys.